All right, so I'm going to walk you through the lab for this week. I'm not even posting another lab thing because I'm basically just going to go through some parts of the homework, and then of course you're going to write the code, your own. You're going to have to write your own code, and then also write whatever the last part is, testing the methods. I think I asked you to do some analysis down there. I can't remember. I should really know. This says fourth part. That says seventh part. It should say fifth part. I think in the homework it says fifth part. I'm working off a slightly old. I'm working off a slightly old version here, but nothing substantial has changed. Okay, so here, anyways. So what we're doing, there's a couple of things we're gonna do. I have given you this matrix. This code right here is to make a certain matrix. If you look at the problems in the textbook in section 3, there's a problem. It's like the first PDE that's listed. This code here builds that problem. So we can sort of have a standard problem to test things on. So this is what you have in your homework. If you run this, basically nothing should happen. I am running this in Jupyter on my own computer rather than Google Colab, because in Google Colab things just take a little bit longer to run, though I don't know how long things might take to run while I'm recording this and doing the code. Here's another code. You don't have this in your problem. That's fine. I'm going to experiment with this later, perhaps in upcoming videos. So you don't have to worry about this, but I'm just going to run it so that we have it. So again, this part right here, all we're doing is we're checking just to make sure that everything that we have done above gives us what we want here. So I changed my output for the build operator. It's just returning the matrix, not the mesh grid, because that's not needed. It typically might be if you're going to plot these solutions, but we're not. So okay, so I'm going to run this, and we should get to see the sparsity pattern. Now this 10 is the size of the matrix, but it's because the idea is that this comes from a two-dimensional problem. 10 is like the number of interior grid points in each direction. So 10 here really results in a matrix that's 100 by 100, so 10 squared. So that's why we have going up to 100 here. We can definitely see that this is a sparse matrix with this sort of block structure that we're familiar with. Okay, so if we want to make it a little bit smaller to see it a little bit more clearly, we can do like this. I guess if you want it 10 by 10 matrix, okay, that's kind of hard to see what's happening there, isn't it? So I'm going to go back to 10. All right, so the first thing that we're going to do is we're going to compute an Arnoldi step. So there's many different ways that you might think about organizing your program. In my mind, the way that I'm going to do it is I'm going to have this Arnoldi step that is basically in charge of updating the V matrix and the H bar matrix. Now, again, you could basically have all of this inside of your FOM or your GM res state, your GM res functions. That's completely fine, but I'm just going to have mine separate. So this is how I wanted to design the program, and this is how I guess I'm sort of forcing you to do it this way as well. But again, you could have this inside your FOM or your GM res code as well. Now, the reason that I chose to do it this way is because it's the same thing used for both ideas, for both methods. So in my opinion, it makes sense then to have sort of abstract and also encapsulate, because one of the things that you'll see in this code is that only the Arnoldi step is going to be modifying the V and the H bar matrix. So the FOM and the GMRes code will call Arnoldi step. It will make sort of blank versions of V and H bar, but it's never gonna those codes are never gonna modify V or H bar. So let's look at this now. This computes one Arnoldi step. So it is this Arnoldi step of getting the next orthogonal vector for the Krylov basis. This is one of the parts of the FOM and the GMRes algorithm. So if you're It's probably best if you have those either written down or if you can look them up in the book to sort of refer to what's happening. But this is going to give you the next vector, that is the next column in the V matrix, and it's going to give you the next column in the H bar matrix. So one thing like maybe that I should have mentioned before, because a lot of our coding involves loops, is when we are writing a computer program that has loops, it's helpful to identify what is sometimes called the loop invariant. That is, it's the thing that is true before the start of every iteration of the loop. It's true at the end of every iteration of the loop, and once you exit the loop, it's the thing that is true that guarantees that the algorithm has the output that you want it to have. Okay, so like for a Fibonacci sequence, if you have a loop that computes a Fibonacci sequence, maybe you have two numbers, one that stores the previous value of the Fibonacci sequence, one that stores the current value of the Fibonacci sequence. So before you go into every loop, those two things need to have the current value of the Fibonacci sequence and the previous value. The code in the Fibonacci loop is going to update that, and then so when it comes out, you've increased the in by the next in you're computing the Fibonacci sequence in. One of those is going to have the previous Fibonacci sequence, and the other one is going to have the current Fibonacci sequence. And then once you exit, the thing that you care about is going to be that last the last term of the Fibonacci sequence. So we're going to ask a similar question for the Arnoldi step. So V begins as a matrix of all zeros. And so one other thing. This loop invariant is sort of parallel to like an induction hypothesis. And so you can prove that your algorithm is correct if the loop invariant stays intact, and sort of by in a sort of mathematical induction way. Anyways, what is it going to be for the Arnoldi step? Well, the idea is that we're calling it with a matrix A, matrix V. That's where we're going to store our vectors, an H bar matrix, and J, and an initial residual. This M right here, forget about that for now. I'll talk about that later. Okay, so what's going to happen then is we assume here, when we come into the loop, it assumes that the first J vectors have been computed and are stored in the first J columns of V. And this is going to compute the J plus 1th vector and store it in the J plus 1th column. Okay, so this is the loop invariant. That on when you call this with J, when you call this with a certain value of J there, you're going to have the first J vectors computed and stored in V, and then when we exit the loop, we need to have the first J plus 1 vectors computed and stored in the J plus 1th column. So in other words, with respect to V, what our code needs to do is leave the first J columns alone and then add the next vector to the J plus 1th column. Okay, for H bar, remember V ends with one more column than H. So V is always going to have like one column ahead of H. So regarding H bar, it assumes that the first J minus 1 columns have been computed, and this is going to compute column J. And so that is the loop invariant. Okay, so when we talk about the algorithm in class and when we're thinking about it in the book and things like that, we have an algorithm. We have our indices that are one indexed, meaning the first index is 0. In Python, that's not the case. The first index, in class and in the book, the first index is 1. In Python, though, the first index is 0. And so this right here is just a restatement of that in terms of indices. So in terms of indices, the above can be restated. Regarding V, it assumes that the columns of V with indices 0 through J plus 1 have been computed and contain the first J vectors. This will compute the jth index vector and store it in the jth indexed column of V. And then I don't know why I've stopped writing it and I didn't write something about H bar here, but I will let you sort of translate the H bar there. Okay, so what are the parameters? What gets passed into the Arnoldi step? Well, the matrix needs to be a sparse matrix. By the way, a lot of people in the projects, I don't know if this is because maybe I did something in one of the labs that was confusing or something, but a lot of people in their assembly function for the matrix A did everything like sparse, but then what they returned was a dot to array, which just made it into a dense matrix. I mean, in a programming sense. Obviously, mathematically, it still has the same number of non-zero entries, but it was done in such a way when you do to array, you're not able to use directly the sparse properties of the matrix. And so a lot of people, the code took a very long time to run because you weren't really using sparse matrix operations. You were doing dense matrix operations. So don't do that for the next project. So A is a sparse matrix. Okay, V is a matrix that contains all of our vectors. Okay, it's the VM matrix in lecture. And H, this is the really this is H bar, so I should write this as H bar here. Just realizing that now. H bar is the H bar matrix from class. Now tolerance is we have to check whether or not this is 0, and tolerance does that. So what is 0? 0 is going to be when it's within 1e minus 14 of 0, or it's when it's within tolerance of 0. Okay, so what is going to return? It's going to return a Boolean that is true false. That's going to tell you whether or not the method broke down. That is like the norm of the next vector that it computed is equal to 0. In other words, it computes a 0 vector. And it's going to return m. That's the number of usable vectors. So ideally, if we're running this, that, you know, if we have a Krylov space of dimension m, then it should return m. But if it breaks down before then, it's going to return an appropriate number based on when it broke down. Okay, so now I have return none. Obviously, we don't want it to return none, but I just have it there so that it you know, so that the code runs when I give it to you. Okay, so the first thing that we need to do is one design decision that you have to make is who is responsible for making V1, because when you hand this algorithm a matrix of all zeros, from that alone it cannot compute the next vector. Okay, so who is in charge of making that first vector? And my design decision, there's other reasonable design decisions. My design decision is that I want only the Arnoldi function to be doing anything with the V matrix. I don't want that being modified by any other part of the code. That way I know that if there's something going on, or if I change something about how I want it to be modified, all I have to do is I have to look in the Arnoldi step. And this is something that will come up, or could come up, probably not in this video, but if I make a sort of more advanced lab video, it might come up there. So we have to handle what happens if we're looking at when j is equal to 0. Because when j is equal to 0, according to the loop invariant, we have the vectors computed from 0 up to j minus 1. Okay, but if j is equal to 0, that means we have no vectors computed. So if j is equal to 0, and as always, if you see me looking to the side, because I'm looking at the other computer monitor, because I have my work that's up there. Okay, so if j is equal to 0, what we're going to do is we're going to set the first column of the matrix equal to r naught divided by its norm. Okay, because that is, if you look at the algorithm, that is the first thing you do. V1 is going to be equal to the residual divided by its norm. So that's what we're doing. And we're going to be using all Euclidean norms here. For this part, it has to be the Euclidean norm for the orthogonality to make sense. Okay, so we're going to do r naught divided by np dot linalg dot norm r naught, like this. Okay, and that, okay, great. And so now we have done this iteration of the loop. There is one usable vector, so we're going to return 1, and it is not broken down, so we're going to return 1 false. And so what's going to happen is our FOM and our GMRes algorithms are going to have loops, and in each loop, or sorry, each iteration of the loop is going to compute the next Arnoldi step. So each time, this is just, so in other words, our Arnoldi step is one, it represents one iteration in a larger loop. So it return at the end of it, but it's a function, so it has to return something. So we're returning 1 false. Now, anytime we're dividing by 0, anytime we're dividing by a variable, there is a chance that something wrong has happened. So what would that wrong thing be in this case? So that wrong thing here would be if this is equal to 0, then if np.linalgnorm is equal to 0. And so what we're going to do here is the following. We're going to check against that. If np.linalg.norm of r naught is less than tolerance, we're going to return 0. There's no that means we've computed no usable columns, and true. Okay, now what this means, if r naught is equal to the 0 vector, it means the initial guess x naught is a solution. So that's great if that happens. From the perspective of the person calling this function, that's great if it happens, but we have to handle it here. Okay, anyways. So also, almost certainly, if the past is any guide, I'm going to make some typos here. If you see that I've made a typo, just hang with me, because I'm going to be running the code every so often to sort of make sure that I haven't made typos. So I'm going to run this just to make sure there's not, the only thing that it would catch would be like a syntax error or something. I am having an annoying time with the tab key though, so all right. So now what I need to do is I need to make my w vector. Now in the algorithm that is depicted in the book, as it's written in the book, it's wj, and then from wj we make vj plus 1. But what we're doing here, what are our indices? Well, if you look back up to the loop invariant here, this will compute the jth indexed vector. Okay, so we are going to wj, so the w that we're going to be computing is going to be based on the wj minus 1 vector. Okay, so the w that we are going to compute is based on the j minus 1th indexed column of v. So instead of calling it wj, I'm going to call it wjm1 for wj minus 1. Okay, you don't have to do that. I'm doing that simply because I want my variables to have names that let me understand what's happening. Okay, so this is equal to a times, and remember the at symbol is multiplication. If it's a sparse matrix, it does sparse multiplication. So this is equal to a times the previous vector. So what is the previous vector? Well, remember, according to the loop invariant, it is stored in the index j minus 1 column of v. So v, and we want the j minus 1th indexed column. So we're going to put a j minus 1 here, and we want all of the rows. And remember, to do that, we just do a colon. Like if I do a to b here, it's going to get the entries starting at index a up to, but not including the entries at index b. So if you just do, if I do this, it goes a to the last entry. If you do this, it goes from the 0 entry up to index b minus 1. If you do this, it gives you everything. Okay. So that's going to be wj. Now we're going to need to know what the norm of this is. Remember, so we're going to call this av norm is equal to np dot linalg dot norm wjm1. Okay, so the if we just sort of do things the way that it has it in the book, we're going to write a loop here, and we're going to say for I in range j. So in the book, it goes I equals 1 to j, where j is, in the book, we've done vectors 1 through j. Here we've done vectors 0 through j minus 1. Range j gives you 0 through and including j minus 1, but not j. So this is the right thing. So for I in j, we're going to say you need to set our hij values. So h bar I j minus 1. Remember, because it's not j in the book, it's j, not j minus 1. But since we're doing index, it needs to be 0 index. It needs to be j minus 1. This is going to be equal to wj minus 1 times the ith the ith column of v, which is going to be v sub I. And so these are going to range from v sub I to v sub j minus 1, which is exactly what it needs to do. And then on each one of these loops, we're going to say wj minus 1 minus equals h bar I j minus 1 times the corresponding vector. Okay, so this is something called this idea is something called modified Gram-Schmidt. Okay, the idea here, what's happening here, is that in ordinary Gram-Schmidt, we like compute all of the h's, and then like this part would be in a separate loop. It'd be in its own loop like this. Hold on. This is classical, a sort of classical Gram-Schmidt setup like this. Okay, the reason that we do it like this is what we want to do is mathematically this and this are the same. Mathematically, these two things are the same. The problem is that in floating point arithmetic, what we're doing here is we're subtracting one vector at a time. We are subtracting the projection of w onto that vector. Okay, that is what the Gram-Schmidt orthogonalization process does. You take a vector, you have a bunch of orthogonal vectors that come before it. You do this vector minus its projection onto the previous vectors, and so you're just left with the part of that vector that's orthogonal to the previous vectors. That is just the basic idea behind Gram-Schmidt. The problem is that in floating point arithmetic, what's going to happen is they're going to be like this isn't going to be exact. And so every time you do this projection, where you do w minus its projection onto the orthogonal vectors, it's not going to come out exact. And you're going to have a little bit of an error term that has directions that is not orthogonal, that is parallel. You're going to have an error term, and part of that error term is going to be orthogonal to the vectors. Sorry, part of that error term is going to be parallel to the vectors that you want it to be orthogonal to. So in other words, mathematically, all you're going to get is a part of the vector that is orthogonal to the previous ones. But since we're dealing with floating point arithmetic, and it's not perfect arithmetic, you always have the potential of having an error that is not orthogonal. So if we have this, if we update it like this, what we're doing then is each iteration of the loop, we're taking that error and re-orthogonalizing it with respect to the vectors before. And so it's a way to sort of keep that error from growing, because we just sort of re-orthogonalize it every single time. And every single time there's going to be another little bit of an error, but the idea is that this way it's not going to build up. We're just going to re-orthogonalize it every single time. Okay, so this is what we're going to have here. This is sort of like the main part of what's happening. Okay, so once we've done this, remember the last thing we need to do is we need to compute the next h value. Excuse me. We need to compute the next h value, and then we need to compute the final v value and store that in the next column. So that's what we're going to do now. But we first are going to make sure, we're first going to see whether or not we have broken down. So I'm going to say h next is equal to np.linalg.norm wjm minus 1. Okay, and so now what I want to do is I'm going to say I want to say something like if h next equals 0, then do something. Okay, then it means we've broken down. Because what it means is that the only part of the next vector that we have computed, the only part of the vector that we have just computed, that, what it says is that there's no part of avj or avj minus 1 that is not, there is no part of avj minus 1 that is orthogonal to the previous vectors. So in Gram-Schmidt, you never have this problem, really, if you deal with linearly independent vectors, but we don't know if we have that here. Anyways, so we have to test for this. Even in Gram-Schmidt, you would test for it. But the problem here is that we don't want actual 0. We want to have h next less than or equal to tolerance. This is what we want. But actually, it's really the relevant quantity is its comparison to the first norm, is its comparison to that. Okay, because if this, for example, is very, very large, and we have h next that is like 1 to the minus 14th, like if the norm of wjm minus 1 is 10 to the power of 14, and now we have 1 e to the 14 here, it's not going to give us the right thing. Like if the norm of this vector right here, the updated wj minus 1, okay, it could be the case that that's equal to 1, but that 1 could be 10 to the minus 14th of what we started with, of the vector that we started with. So in other words, in a sense, yes, there's been a breakdown, because compared to 10 to the power of 14, 1 is basically 0. So what we do here is tolerance times the norm that we started with, AV norm. Okay. So this right here, this is the breakdown case. So if this is less than AV norm, we're going to say h bar. We still have to set this h bar j minus 1 is equal to np dot linalg well, it's just h next. Sorry. Like this, and we're going to return j and true. Okay, because we have put the next vector in V. So we put the vectors there, and we've got j usable vectors. Notice something that's important here. We're going up to j minus 1 for h here. Okay. So, yeah, all right. So in the case of breakdown, we're still going to have the case where h bar has like one less column than V. That was why I said that. Okay. If that doesn't happen, then we're just going to say h bar is the same thing no matter what, really. H bar. And so since we're doing the same thing in each branch of the code, we should probably, and I'm saying we now as if you guys are somehow doing this as well. This computation here should probably be taking place here, since we do it. I have it done whether or not we are in breakdown or not. So anyways, just something I noticed as I don't know why I didn't catch that before, but anyways. Okay, so if h next is not less than or equal to this, in other words, it's not equal to 0, it's now safe to divide by it. So now we're going to say wj minus 1. Remember, we need to just divide it by its magnitude. So wj minus 1 divided by h next. And I think if you want, you can do divide equals h next. But just for the sake of whatever, I'm going to keep it like this. Okay. And then now we need to set the next column. Remember, it's the jth index column that we're setting. So V, all of the rows, column J is equal to Wj minus 1. So notice what we've done. We have set the jth index column of V, which is exactly what needs to happen. This computes the jth column of h bar and stores it in the jth column of h bar. This is one indexed notation, so 0 index would be the j minus 1 column, and it computes the j minus 1 column of h bar, and that's exactly what we've done here. And notice this j is one more than that, which is exactly what we would expect. So I'm now going to run this. No syntax problems there. And now this is going to be where we test it. So I've got n is equal to 10. So this is going to give me a 100 by 100 matrix. M is equal to 4. So this means that V is going to be a 10 by 5 matrix, and H bar is going to be a 5 by 4 matrix. So now we need to test this part. So we have we're gonna verify that it satisfies the Arnoldi relation. So I'm gonna make a my matrices of 0. So again, What does V need to be? It needs to be a matrix. Its dimensions need to be, I said 10, but it's 100. So remember the size of A is 100, 100 by 100. So then V needs to be a 100 by 5 matrix of 0. So NP dot zeros, and the size n times n. This is because, again, that's the size of A. It's the size of the number of unknowns. And then n plus 1. And then h bar is going to be equal to np dot zeros, and its size is going to be m plus 1 by m. So m plus 1 rows by m. Okay, that's exactly, what the code says, what the algorithm says. Let me just run this, make sure I haven't screwed anything up there. All right, so now I'm going to make a true vector. I'm not going to do that yet. I haven't made a true vector yet. We're not even to the part on testing this on a system of equations, so never mind that part. What I am going to do is I'm going to make a vector, just a random vector. So it's going to be np dot random dot standard normal, and the length is going to be equal to the length of a dot shape 1. Is that what I want? Well, it's a square matrix, so it doesn't matter. But I want it to be equal to the number of columns of A, because I'm going to be doing A times this, so it needs to be equal to the number of columns. So it's square, so mathematically these two things are the same, but conceptually it should be that the number of entries in X naught should be the number of columns of A. While I'm at it, this V right here, I'm just going to do as A. I think it's a little safer to do A dot shape 0. Now, this we're going to have A times V, so the number of rows of V should be equal to the number of columns of A as well, so I'm going to make that 1. Okay, again, mathematically they're the same, but conceptually this is how we should think about it. Okay, right, because here we're doing A times V, and so we need to make sure that the number of rows of V, which is equal to that first entry there, is the same as the number of columns of A, which is A dot shape 1. Okay, so let's just make sure we're okay here. Very good. And now R naught is going to be equal to A times X naught. It's going to run this to make sure I haven't done anything wrong. And now what we're going to do is we're going to have our loop that's going to compute the Arnoldi steps for J in range n plus 1. Now notice what I need to do. I need to do the loop m plus 1 times. J in range gives me 0. Sorry, J in range m plus 1 is going to give me J from 0 up to, but not including m plus 1. So in other words, it's going to give me J's from 0 up to and including m. And the last column of V is going to be like our orthogonal vector that we're not going to use. It's just the first m columns of V that are going to be that are going to give us an orthogonal basis for the Krylov subspace. Okay, so now we're going to do Arnoldi step. A, V, H bar, J, R naught. Okay, and notice that we are not updating V or H bar. We have all of that in the Arnoldi step. We're only allowing the Arnoldi step to update V and H bar. Okay, so before I check these Arnoldi relationships, I'm just going to run this, print H bar, and I should get a Hessenberg matrix. And I didn't. What went? Oh, AV norm. What happened here? See, this is one of those typos that you guys were probably like, there's a typo, there's a typo. Okay. Yep, okay, and notice this is in fact a Hessenberg matrix, so bam, bam, underneath it is 0, bam, 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 underneath it is 0, bam, 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 underneath it is 0, and all of these, okay. And we can also tell right away, since the matrix has this shape, it's also not singular, which is good because we're going to need to be doing the inverse of it. Okay, so this is perfect, beautiful. So now what I want to do is I want to test this relationship right here, but I have to think through things. So the V matrix that I have now, the V matrix that I have now, is really like Vm plus 1. That's the matrix that I have. Okay, in within V is the matrix Vm plus 1 because you've gone one more step. So you for the Arnoldi algorithm, remember you compute one extra vector than you need for a basis for the Krylov subspace. So you end up with m plus 1 columns. So Vm plus 1 is what is in V right now. So what I need to do, I'm just gonna type out the product that I need. So I want to do like AVM minus Vm plus 1 times H bar. So what is AVM? Well, it's going to be A times V, and I want everything up to the last column, or up to but not including the last column. So I could write it like this: B, comma, minus 1. That's what this is going to give me. It's going to give me everything up to but not including the last column. Minus 1 gives you the last column. If you have it in the right index, it goes up to but not including that. Okay. You could also put an m there as well. Okay, then we're gonna do minus. Now H bar is exactly this matrix here, because remember, just as we saw in class and as I've said several times already, H bar has one less column than V does. Okay, so we're good here. So now we're just going to have V at H bar. I'm just going to run this just to make sure this product makes sense. Wow. What happened? Wonderful. No. I don't know what is going on here. Oh, come on now. Let me save this. What? Okay, let me restart this or refresh it. Great. Okay. Hopefully I did not just lose everything. Okay, that looks okay. All right, I think that's what I want here. Oh, I see, because why? Oh, okay, that's what happened. Okay, well, of course, everything worked fine. And each time you run it, since I'm not seeding the random number generator, it's going to be different, but that's fine. Okay, and now what I want to do is I want to measure the maximum difference between these two. So np.abs is going to be something like this, and then I want to do np.max, and actually I want to print this. So print max diff is okay. And that's what we have here, 2 to the power of minus 11. Or if I want to put an m here, I could write it like that. So this is basically 0, right? Which is, it shows, this is just a test to make sure that our Arnoldi step is working. Because we want to make sure our Arnoldi step works before we plug it into our FOM or to our GMRes functions. Okay. So FOM, let's move on to that part now. Okay, so remember what's happening with the full orthogonalization method. What this does is it makes a guess at what the let's also forget about p equals none for now. What it does is it makes a guess, and then it forms the residual, and then makes a Krylov space based on that. And then once it makes the Krylov space, once it's done doing that, what it does is it then looks for a solution in that Krylov space. So that's what's happening here. The main the main loop is just going to be calling this Arnoldi function. But there's unfortunately a bunch of irritating things that we kind of have to get out of the way before we can get to that. Okay, so let's do that. One thing that I am going to add, maybe I don't have it here. I'm going to add, in addition to tolerance, I'm going to add rtol. And what we need to do, it makes more sense. Well, the reason that it doesn't matter here, never mind. So we'll get to relative tolerance in just a moment here. Yeah, we'll get to, this is actually going to be a little bit different, so I will talk about that. So sorry. I've done multiple versions of this getting prepared, and I forgot which version I want to start with. There's actually something else I want to come up here to the Arnoldi method, and talk about that I wanted to mention. This right here can all be vectorized. So this loop here can be vectorized. So if we think about what's happening here, if we conceptualize it like this for I in range j, if we think about doing this, if we think about doing this in two separate loops, it makes it a little bit more clear what's happening. This first loop right here, notice what we're doing. Well, this is a vector, and we're doing it times this vector here. So we're doing dot products here, and we are coming up with an h. So what we're doing then, so when we're doing dot products, let me even write it like this to make it. Okay, we're doing the dot product of the 0th column with this, then and storing it in one entry, in entry 0. Then in entry 1, we're doing the 1 index column of v dotted with this, and that's going to give us another number, all the way down to the last one. When I is equal to j minus 1 is going to be the dot product of the j minus 1 column of v with wj minus 1. So in other words, what we're doing, anytime you have a bunch of dot products that you're doing, you can write that as a transpose of the corresponding matrix times the vector. So this part right here, for I in range j, we can say, we can do the following. We can say h1 is equal to v. Okay, we want to look at the first j columns, that is columns from index 0 up to index j minus 1, and all the rows. So this is going to give us all of the rows, and then here if I do colon j, this is going to give me the indices, all of the columns up to but not including index j, and then times, I need to do the transpose, dot transpose, and then times vj minus 1. So this right here takes the place of this. Okay, well, I have a problem here. Oh, I don't know. Here we go. That's what I meant. All right. Oh, yeah. Okay. There we go. Now I'm just going to test this to make sure. Okay, this is not right here. It should not. This is good, but we should not have a diagonal matrix. So the question is, where did I go wrong? Oh, because I never stored the yeah, okay, hold on one second. Oh wait, now this is a little bit confusing here, where okay. Oh, because I haven't set anything. I haven't set h to the thing that it needs to be yet. Okay, so here we're setting h as we go. So now I need to set that the j minus 1th column of h equal to h1. But it's not just going to be the whole column of h. So remember, h bar has m plus 1 rows. So I need to set the first j entries, or indices 0 to j minus 1 of the jth column of h bar. So I'm going to have h bar, I'm going to go up to j, and then I'm going to have j minus 1 is going to be equal to h1. Okay, so now let's try this. Okay, there we go. This is still Hessenberg, so all right, I feel comfortable there. And now we have this. But notice what we're doing here. This is a linear combination. This is a linear combination of vectors. And anytime you have a linear combination of vectors, we can always do that as matrix vector multiplication. So what we're doing here is we're doing I is going to go from 0 to j minus 1, and then we're multiplying it by this. So what we're doing then is we're just multiplying the V matrix by the appropriate column, the first j entries of the j minus 1th column of H bar. And so we can write this in the following way. We can say Wj minus 1 is equal to Wj minus 1 minus V. We want to look at the first j columns of V. So that is the columns from index 0 up to index j minus 1. And we're going to multiply it by h1 like this. Okay, and we're saying Wj is equal, Wj minus 1 is equal to Wj minus 1 minus that. So in other words, if we think about what's happening here, we have V times h1. What is h1? V is V transpose times W. So overall, this is W minus V times V transpose times W. Well, V transpose W is a projection of W onto the previous vectors. So mathematically, this makes sense. I'm going to run this. And again, we get everything like we wanted to. Now, one thing to point out here is this method right here is a standard Gram-Schmidt algorithm. So in other words, it's exactly what I talked about before, where we have split these two things up. So what's going to happen though is in this procedure right here, because these things are not exact up here, this procedure right here, we're not doing this reorthogonalization that we talked about down here. We're not reorthogonalizing this one against the other ones, against the previous ones. So there's one thing that we can do to fix this problem. I have not noticed that it is a problem. With what we're doing in this class. But what we can do is the following. I'm going to move this down here. What we can do is what's called reorthogonalization. So we have this, and now what we want is we're going to do this again. We're basically going to do the same exact thing again. We're going to say H2 is going to be equal to this. So notice what H2 is. H2 is V transpose times Wj m minus 1. Now the whole point, mathematically, Wj minus 1 is now orthogonal. Like after this line, in perfect arithmetic, Wj minus 1 is orthogonal to all of the V vectors before. So this right here should be 0, because it's the projection of Wj minus 1 onto the previous vectors, but it's equal mathematically in perfect arithmetic, that's equal to 0. But we don't have perfect arithmetic, so this is now basically what we're doing is we are getting rid of that error term. Okay, so now what we're going to have is this is going to be H2, and now we're going to say this same exact thing again. This, except we're going to have H2 here. Okay, now what do we put in H bar? H2 should be equal to 0, but it's not going to be exactly equal to 0. So if we run this, we'll get something. Oh man, see, it's 1 order of magnitude less good. Well, not even all the time. Okay, so what's happening in this case is in our formula we have W. The W that we have is going to be W minus W minus V times H. So that's what we have here. W minus V times H. And for the Arnoldi relationships to make sense, the column that we store in the next column of H needs to be the H in V or W minus VH. So again, what we have here, the updated W is going to be the old W minus V times H. Okay, that's what the algorithm here says. The updated W is going to be the old W minus V times H. Okay, so what does that mean for the Arnoldi relationships to make sense? That thing that goes there that thing here needs to be stored in the next column of h bar. But notice we've done this twice. And if you work through all of the formulas, what this becomes then, overall, this formula here becomes mathematically W minus V times H1 plus H2. So here we need to have H1 plus H2. Now, like I said, this has not, in my experimentation, this has not made a difference. It looks like we're consistently at 10 to the minus 11th, whereas before, without that, we were getting to 10 to the minus 10, which is one order of magnitude less good or whatever. For our purposes, that has not been a problem for me. The other thing is that when the dimensions get big, when n, that is the size of A, and m get big, then what we have happened is that this step here takes a whole lot of time. So what I'm going to do is I'm just going to comment these out so that we just have the standard Gram-Schmidt process, but I just want to point out that sometimes we have to do this reorthogonalization. And it might make sense to do a test, and if the test doesn't pass, if we have a vector that is not orthogonal enough to the previous vectors, then maybe we reorthogonalize. So instead of, here we don't reorthogonalize at all, and that could cause problems. Here we reorthogonalize every time, and that could take too long. You could have some sort of dynamic thing, and you reorthogonalize when you need to, but if you don't need to, then you don't reorthogonalize. Okay. Anyways, so I'm going to keep it like that. Simply because for all of my experimentation for the matrices that we're dealing with, it hasn't been an issue. Not to say that it is never an issue. It definitely is an issue sometimes. Okay. All right. I think that video is probably going to be a good length for now. So I'm going to stop this video, and then in the next video, I'm going to show you how we're going to implement the FOM cycle and the GMRes cycle.